We have, what I want to do is kind of go a little bit in some of the notes that cover Unit 2, and more specifically Part G. These are the equations that we will need that will be very beneficial to us as we see it and as we need it. Make sure that we have these written down. So let's use this first example as an opportunity to practice some things. An apple drops from a tree and hits the ground in 1 second. What is the speed upon striking the ground? What is the average speed during the 1 second? How high above the ground was the apple when it was first dropped? Now, one of the things that we need to pay attention to is the order in which the questions are written does not always mean it is the order in which we do the problems. For example, we know a few things. Okay, I'm going to draw this very rudimentary picture of an apple tree. And so let's put our apple in it. Right? At this time, we do not know the distance in the y direction. We do not know that. The only thing we do know is that time is 1 second. We also know, but it's not given to us, and this is usually where problems start approaching. Gravity is always there. And that's at 10 meters per second per second. Now I bring up that information that we do not know the distance in the y direction, and that's very important because we say that the velocity is equal to distance divided by time. We can't find the average speed until we know the distance. We can find some other things out though. We can find the final velocity, even though we are also asked to find the average. And the line above the V tells us the average. The equations that we need, v sub Fy is equal to G times T. D is equal to 1/2 G T squared. And we will need the equation velocity is equal to distance divided by time. The first thing that we can solve for, or the order that we might solve for these, might be a 1, 2, 3. That's not a bad idea to take, is into what order do I need to solve things? What do I know that I can use to help me solve something else? The speed at which it strikes the ground, that's that one. The distance that it takes will be the second. And then the third, because we don't know the distance until it actually we solve for that. So when we go in and we solve for this, gravity 10 meters per second times 1 second tells us that the final velocity in the y direction is 10 meters per second. 10 times 1. Using the second equation, which might be the little bit more difficult, we still have to use some things, and that we have 1/2 times gravity, which is 10, times our time, 1 squared. Now that is going to equal the distance in the y direction. Now 1 squared is going to just give us 1. Times 10 is going to give us 10. Times 1/2. Now we can either write it as times 1/2, or we can write it also as divided by 2. So now we can see that the object fell 5 meters. Now that we know the object fell 5 meters, and it fell that 5 meters in 1 second, would tell us that the average velocity is 5. Now, the average takes into account all of the, let me use a little bit different color here, all of the moments in time that it takes that apple to fall. When an object is dropped, it is not going 10 meters per second right away. It speeds up to that. Think of it as just as the object is rolling down a ramp. It does not speed up all the way to that point right away. So that in itself is a very important concept. Graphically speaking, we know that acceleration would be constant, which means the velocity time graph would have this nice direct way of writing it. And if we took the rise over the run in this problem, rise of 10 divided by a run of 1, we get 10 meters per second. Because if we write it out, a rise of 10 meters per second divided by 1 second gives us our value for gravity of 10 meters per second. So that's where they get this. Now, if we looked at our velocity time, our distance time graph, it might not come out as easy. Actually, probably very difficult to see. because of the curvature that it has. But if we took our slopes of our slopes, and if you wanted to, you could do two derivatives to find that, but that's something for people that take calculus and not for us. So speed versus time is a direct proportional. A parabolic or quadratic is the distance time graph, because time needs to be squared. Time needs to be squared. So it is non-linear or not direct. It is quadratic. That curve tells us that it's quadratic. Now, air resistance we know has a thing. And now what's going to be very nice for us is that we are going to try to limit air resistance or negate air resistance as much as we possibly can. Because with air resistance, we know that an elephant and a feather will not fall at the same rate. One falls faster with air resistance. Many of the experiments, laboratories that are done in class, you can eliminate air resistance as much as you want to. It will be there, but we will take it out of the equation because it really does complicate things greatly. There are things that can be done to limit air resistance, but we are just going to say, yeah, we know it's there, but we won't deal with it. In a vacuum, and this is what problems people, in a vacuum, meaning the absence of air, the acceleration due to gravity, or G, is the same for everything. Meaning that the objects will fall at the same rate. All objects fall at the same rate in a vacuum. And for this class, we are going to go under the impression that we are dealing with a vacuum even though we have air. It will make our calculations much easier to deal with.